This modern physics lecture is on energy level diagrams. I'm Mrs. Estock. Let's get started. For thousands of years, scientists have tried to improve upon our model for the atom. In 1911, Ernest Rutherford conducted his famous gold foil experiment, where he shot a stream of alpha particles at a piece of gold foil. And what he found is that while most of the alpha particles passed right through the gold foil, some of them were deflected or scattered at large angles. What he concluded from this result is that since most of the alpha particles passed right through the gold foil, that must mean that the atom is comprised of mostly empty space. But if some of those positively charged alpha particles got deflected, they must have been deflected by a massive and positively charged nucleus. So from these results, we were able to draw a new model of the atom where the nucleus had a positive charge and it had most of the mass contained with within the nucleus, and it was very small and densely packed. And he imagined that the electrons existed in the space surrounding the nucleus. But in this model of the atom, there was no placement for these electrons. There weren't specific locations or energies that they should be at. So this model, although it was better than the previous model, the plum pudding model, still had some issues that needed to be addressed. For example, as the electrons orbit the nucleus, since they are accelerating around the nucleus, they have to, according to the laws of physics, give off energy in the form of electromagnetic radiation. Well, if they're giving off energy, the electron itself in this process would lose energy. And if the electron loses energy, it's going to get closer and closer to the nucleus and eventually spiral into the nucleus, and that would not be good. We know the electron stays at a certain distance away from the nucleus. It's not going to spiral into the nucleus. So this doesn't actually happen. So Rutherford's model didn't explain how the electron is able to maintain its position outside of the nucleus and not eventually spiral into the nucleus. So that was one problem with the Rutherford model. Another problem is that, as I said before, as that electron orbits the nucleus, it's accelerating because it's moving in a circle and it gives off energy in the form of electromagnetic radiation. If that electron could exist anywhere, if it didn't have a specific energy level to be stuck in, it could, in theory, emit electromagnetic radiation of all wavelengths, a continuous or smooth spectrum, which would look like all of the colors of the rainbow. But that, in fact, is not what we see. For particular elements, we see that there are specific spectral lines. So these wavelengths occur in units and chunks. They don't occur as one smooth, continuous spectrum of wavelengths. So we don't get all the wavelengths. In other words, we get certain wavelengths. So the person who was able to answer these problems and come up with a new model for the atom was Bohr. The Bohr model of the atom was put out in 1913, so just a couple years after Rutherford. And the way he addressed the issues of the Rutherford model is Bohr gave his model of the atom distinct electron orbits that we call energy levels. And each orbit has a specific amount of energy. So if an electron exists, let's say, in the first shell or ground state, it has a particular energy, an exact amount of energy. If the electron exists in the second or third shell or the second or third energy level, those have different but specific amounts of energy. These specific amounts of energy solve the issues that we addressed with the Rutherford model. Now, to make sure we have our terminology correct here, atoms have distinct electron orbits that we'll refer to in this class as either ground state, excited state, or ionized. In ground state, that's when an electron is in the first or the lowest energy level. An excited state is any energy level above ground state. So an excited state electron would have more energy than a ground state electron. And if an electron becomes ionized, it has acquired enough energy to disassociate from the atom. So it becomes a free electron and maybe picked up by another atom, but it's almost like ejected from the atom, and the atom itself has become ionized. Now, in physics, you're going to see this represented on your reference table in the following format as an energy level diagram, where each line represents a particular energy level or electron orbit. Ground state will be at the bottom. That will be the lowest energy level. You can see that the energy levels on the left-hand side of this diagram in electron volts start negative and they work their way to positive. So ionization would be 0, and anything below that would have less energy and represented as a negative value of energy. Speaking of energy, let's make sure we understand the units of energy that we'll be using for these energy level diagrams. Now, we should know that the SI unit for energy is the joule. The SI unit for energy is the joule because if you take 1 joule and break it down into its component parts, it's made of 3 different SI units. 1 joule is equivalent to 1 kilogram meter squared per second squared, where kilograms are a unit of mass, meters, length, and seconds, time. So those 3 SI units combined together give us our definition of the joule. Now, we use the joule when we're talking about the energy of everyday objects on the scale of people and our everyday experience. For example, a person taking a leisurely stroll might have a kinetic energy of about 100 joules. So we can use joules to represent values on a larger scale, but if we tried to use joules on the atomic level, the values would be so small that they'd be a little cumbersome to write because the power of 10 would have a relatively large negative exponent. So since we're talking about tiny amounts of energy, physicists use a different unit to talk about the energy of electrons, and that unit is called the electron volt. So the unit for energy used at the atomic scale is the electron volt, which is defined as the energy required to move an electron across a potential difference or voltage of 1 volt. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, or if you wanted to flip that around, 1 joule is equal to 6.25 times 10 to the 18 electron volts. These 2 values are given to you on the front page of your reference table, and you should be able to convert back and forth between these 2 units. If we look at our reference table, you have 2 energy level diagrams that are given to you. And if you look at the energies, both are in electron volts, abbreviated as E capital V. So I'd like you to imagine all of the energy values on the right-hand side of these diagrams to have units of electron volts. When we're working with these energy level diagrams, a good analogy to think about is the ladder analogy. So say that you're an electron and you're trying to climb up the energy ladder. If the electron starts at the bottom rung, it starts in ground state, and it can move up to a higher energy level by jumping from one orbit to another. Electrons can jump one energy level at a time, or they can even jump multiple energy levels at a time. So I could go from n equals 2 to n equals 6 if I have enough energy. Electrons can also move from a higher energy level to a lower energy level. So as electrons move from one orbit to another, you can imagine that electron almost like climbing up and down a ladder. This is the ladder analogy. Well, how are electrons able to jump from one energy level to another? You can't just gain or lose energy out of nowhere. Where does it come from? Well, that energy comes from photons. Remember, photons are the force carrier particle of the electromagnetic force, and electrons have electric charge, so they're able to emit or absorb photons of light. For an electron to move from a higher to a lower energy level, that electron must give off or emit energy in the form of a photon. If an electron was to move from a lower to a higher energy level, it must absorb energy in the form of a photon. So here's a quick animation of what that might look like. As the electrons move from one energy level to another, they're either absorbing or emitting photons of light. In this model of the atom, we imagine that these jumps from one energy level to another occur instantaneously. So the electrons themselves don't exist in between the energy levels. They make an immediate jump from one energy level to the next. The size of that jump depends on the energy of the photon either absorbed or emitted. And whatever the energy level jump is, the electron has to absorb or emit a photon of energy that is an exact match to the difference between the electron's initial and final energy levels. If the energy of that photon does not match the difference in energy levels, then the jump cannot occur. So again, it has to be an exact match in the difference between the electron's initial and final energy levels. We can find what that value is using the following formula, which is also on your reference table. The energy of that photon, whether emitted or absorbed, has to be exactly equal to the initial energy level minus the final energy level. Here's an example of how that works. Let's say you have a hydrogen atom, and that hydrogen atom emits a photon as an electron changes from energy level 4 to 2. So this electron is emitting a photon of light as it transitions from n equals 4 to n equals 2. On my energy level diagram, I locate the initial and final energies of the electron, and to determine the energy of the photon emitted, I take those two values and I subtract them. So by taking the energy of the electron when it was in level 4, negative 0.85 electron volts, and subtract it from the energy the electron has in its final state in n equals 2, negative 3.40, I can solve for the energy of the photon emitted, 2.55 electron volts. And that energy will be an exact match to the transition between the two levels. So it has to be equal to 2.55 eV. It couldn't be 2.5, it couldn't be 2.4. It has to be exactly 2.55 eV. Otherwise, the electron cannot jump from one level to the next. We have seen this model work with evidence from line absorption and emission spectra. This is something that we will do together in class as well. Because atoms can only emit certain energies or frequencies of photons that correspond to these energy levels, it gives elements unique spectras or unique spectral lines given their electron shell configuration. And if you remember from chemistry, the entire periodic table is organized by how these electron shells' energies are organized. And that's what gives rise to the unique properties of each element. For example, hydrogen has a unique absorption and emission spectrum because of the way its electron shells are set up. Those specific energies give off specific photons of light with energies related exactly to the energies of those electron shells. So this allows scientists to look out into our universe, and depending on the spectral lines that they see, we can identify what our universe is made out of. So we talked a bit about the James Webb Telescope. By looking out into the universe, we can detect what other planets or galaxies are made of. Oxygen, neon, hydrogen, all have unique spectral signals. So we can look out into our universe and know a little bit more about it, just based on how the electrons of particular atoms are organized, thanks to that Bohr model of the atom.